Good afternoon. Many thanks to the organizers for putting together this conference and bringing together a really diverse group of scientists working with ALMA. So my name is Tanmoy Laskar, and I'm a postdoc at Radboud University in Nijmegen in the Netherlands. And I'll be talking to you today about how we can use ALMA to study transients. So what you see here on the title slide is an artist's rendition of a relativistic transient. And this particular illustration was actually part of a press release for an exciting result with ALMA, and I'll be returning to this later on in my talk. Now, since there aren't many talks on transients at this conference, I thought I'd begin with some background on what relativistic transients are and why we like to look at them with ALMA in the first place. So I'll discuss what we found also with the 4 case studies. I will show you the first ever light curve of a transient that we obtained with ALMA and the farthest transient seen by ALMA, which is a gamma ray burst at a redshift of 6. I'll show you how ALMA's fantastic polarization sensitivity is opening a new window in this field. And then finally, there'll be one surprise at the end, which is work in progress. As we go along, I'll try to connect with what we've learned in terms of the associated astrophysics, and then touch on where we are going in the next few years. So just to bring everyone on the same page, when I say relativistic transients, I'm talking about catastrophic stellar explosions that release in a few seconds as much energy as the sun does in its lifetime. So these are extremely luminous, and they can be seen very, very far away. So these transients are powered by the interaction with the ambient medium of a small amount of material that's moving at relativistic speeds, that is close to the speed of light. Now, the large energy budget usually means that these events have jets of some sort. So there is an explosion, stuff is flung out, that stuff interacts with the environment, usually producing a shock, and then there's light, either from the shock or from processes that are happening in the ejecta itself. And then finally, that light reaches us, which we identify as an explosive transient. So examples of such transients include gamma ray bursts. These are the most luminous explosions in the universe. They completely outshine the entire sky in gamma rays for a few seconds. We find these in star-forming regions of galaxies and almost always associated with supernovae, which tells us that they come from the deaths of certain kinds of massive stars, though we don't know yet which ones. At visible wavelengths, these events shine brighter than the combined light of their entire host galaxy, and so they are excellent beacons to light up the dark ages in the history of our universe, which makes them one of the most promising tools for probing the formation, or at least the deaths, of the first generations of massive stars. Now, we now know that there are at least 2 distinct kinds of gamma ray bursts. Those that come from massive stars seem to have gamma ray flashes that last several seconds, but then there's also a population of bursts that are much shorter, from tens of milliseconds to a fraction of a second. And we think that these come from the mergers of compact objects, such as 2 neutron stars or a neutron star in a black hole. Now, these systems are born from binary stars. Each star in that system must originally have been massive enough to enter a supernova. The binary has to survive the 2 supernovae. And then, as the system loses energy and angular momentum to gravitational wave radiation, the compact objects spiral into each other, and after millions of billions of years, they collide and merge, producing a gravitational wave transient along with a gamma ray burst. But we think that the debris from such mergers may be responsible for the production of a large fraction of heavy elements like gold and uranium in the universe. But there's another way in which stars can meet fiery deaths, and that is if they stray too close to the supermassive black holes at the centers of their galaxies, or their host galaxies. So the hapless star gets ripped apart due to tidal gravity of the black hole, and the black hole, after it has had a snack, has a bit of a burp, launches an outflow. And so these tidal disruption events, or TDEs, like gamma ray bursts and gravitational wave transients and supernovae, offer us another excellent place to probe extreme conditions in the universe. So some of the questions that I and others in the community studying energetic transients are currently exploring, we want to know, how fast are these outflows? What are they made of? What is the nature of the central engine that launches these outflows? And how are the jets collimated into narrow opening angles only a few degrees wide? What causes the great diversity of these explosions, from quasi-spherical explosions like relativistic supernovae to highly jetted events like gamma ray bursts, and perhaps with tidal disruption events somewhere in between? And finally, as these events have to do with stars, and particular massive stars in one way or the other, then what do they tell us about the history of star formation and chemical enrichment of the universe? So to see how we can use observations of relativistic transients to explore some of these questions, let's for a minute take a closer look into what goes on inside one of these. Some sort of cataclysmic event, say a tidal disruption of a star by a supermassive black hole, produces a relativistic outflow, either a jet or a wind, through a process that we don't fully understand. Then shock waves inside the outflow sometimes produce gamma rays, in which case we have a gamma ray burst. The interaction of that outflow with the surrounding medium produces two shock waves. The first of these is the forward shock, the blast wave shock, which propagates into the ambient medium. And that shock powers the X-ray to radio synchrotron emission that can last for days, months, or even years. At the same time, a shock wave goes backward through the jet and lights up the jet itself. And both shocks accelerate electrons and produce synchrotron radiation, which we observe as a superposition of two spectral components spanning from the radio to the X-rays. So the forward shock tells us the explosion energy and the environment density. On the other hand, the reverse shock tells us about the outflow properties, its radial structure, its speed, its magnetization. And over time, the emission from both these shocks shifts to lower frequencies and also fades, which means that we need data spanning many orders of magnitude in frequency and time to understand the physics of the system. So how do millimeter band observations like from ALMA help us? First, they bridge the centimeter and the optical, and so they allow us to sample the peak of the spectrum, which is sensitive to the explosion energy and the environment density in the case of the forward shock, and to the outflow Lorentz factor, so the outflow speed in the case of the reverse shock. And there's really no other way to measure the speed of this outflow than to look for this signature of the reverse shock. The millimeter band is also typically above this steep cutoff here, caused by synchrotron self-absorption, which actually can make the millimeter band emission brighter and easier to detect than at the centimeter band. The millimeter band is also unaffected by radio scintillation. So here, for example, is a simulation that shows how much better we can constrain the energy and of the outflow and the density of the surrounding medium from forward shock measurements if we include millimeter band data. So we get the constraints that are shown in black compared to what we get if we just had X-rays and optical, that's in blue, or if we had X-ray and optical and centimeter band light fields, that's in orange. The millimeter band is also a very good probe of the density structure of the environment. So these two models shown in the red line and the blue dashed line, with different density structures, are almost indistinguishable at, say, 5 gigahertz in the centimeter band, or in the X-rays, or in optical bands. But it's quite easy to tell them apart in the millimeter band, especially with early measurements. So we can understand the radial structure of the density around whatever it is that is exploding or producing an outflow. And finally, the millimeter band is also a good probe of intrinsic polarization, which has information about the magnetic field structure of the outflow. So here's what we know about relativistic transients in the millimeter band. These are most, if not all, of the 3 millimeter observations of relativistic transients that we have. Most of these are gamma ray bursts. All of those are the long duration variety. In gray are the observations from facilities before ALMA. And in the colored circles are the gamma ray burst light curves that we collected with ALMA. The stars at the top here are 2 relativistic tidal disruption events. The first of which in black is from 2011, so pre-ALMA. And we are very excited that there's potentially the second one that is announced just a couple of weeks ago. And it's been reported to have a very bright millimeter counterpart from other facilities. And so we are waiting for ALMA to observe it for us. So this event is actually the most luminous millimeter transient in the corresponding West frame time, which is pretty cool. So in the remaining time, I'm going to walk you through some highlights from these ALMA observations. So this one, this GRB 161219b here in brown, this is the first ALMA light curve of a gamma ray burst afterglow. And as far as I'm aware, it's the first ALMA light curve of a transient. So the ALMA light curve for this event has 2 contributions. The late emission after about 10 days comes from the forward shock, which we can also constrain from the optical and X-rays. The early millimeter band emission here is in excess of the contribution or the expectation from the forward shock, and that can be understood as a reverse shock. But all the models that you see in this talk are from a modeling software that I wrote for my thesis. So the combined model that I'm showing you here explains the millimeter band light curve fairly well, but it fits not just the ALMA light curve, but also the X-ray, UV, optical, and near-infrared data from 10 to the 9 hertz to 10 to the 17 hertz over 5 orders of magnitude in time. Now, in this case, this reverse shock that we are seeing is continually refreshed, which means that we're seeing evidence for lower and lower Lorentz factor material that's piling on to the jet at later times. It's suggesting that there's radial structure in the jet, or material traveling at different Lorentz factors, from Lorentz factor of 100 to a Lorentz factor of about 20. This was the subject of an NRO press release, though not the one that I mentioned in my title slide. That one is from the ALMA work that I'm going to describe next. So let's talk a bit more about what these reverse shocks can tell us. Now, if these relativistic outflows contain ordered magnetic fields, then this reverse shock emission is expected to be polarized at levels of up to several tens of %. Now, probing this reverse shock polarization, radiopolarization signature has not been possible with past facilities. And so here are some of the best radiopolarization upper limits for gamma ray bursts from the literature in the centimeter band, that's at gigahertz frequencies. And the centimeter band is unfortunately not great for polarization studies because reverse shock emission is usually self-absorbed in the centimeter band, and self-absorption can depolarize the light. Now, with ALMA, for the first time, we have the ability to study polarized reverse shocks in the millimeter band. So this is the band 3 Stokes I light curve for the gamma ray burst that I was just showing you earlier. And these observations from 2016 were actually taken before polarization observations were commissioned at ALMA. The orange band here represents the expected polarized flux if the emission were somewhere between 1 and 10% polarized, compared at the bottom to ALMA sensitivity, highlighting that we need to get on target quickly, especially if the target has low polarization fraction below 10% or up to 1%. Now, as luck would have it, we had the perfect opportunity in January 2019, where we triggered ALMA polarimetry observations beginning 2 hours after a gamma ray burst and obtained the first ever detection of radiopolarization in a GRB. So here are the images from snapshots spanning a few hours after the burst, and you can see a clear detection in Stokes even U, as well as some temporal evolution. And here's the same data in the form of light curves. The blue points at the top are the Stokes I light curve. In the lower panel, I've plotted the linear polarized intensity, which clearly decreases with time. And there's also some evidence that the polarization fraction decreases as well, from 0.9% to 0.6% over the course of a couple of hours. And during this period, the polarization position angle rotates from 10 degrees to minus 45 degrees. But this itself was an exciting result, but we went one step further. We also got VLA observations as the source rose over New Mexico, and we actually have simultaneous observations at the VLA and ALMA during the time of our ALMA polarization measurement. We found that the X-ray and optical data at that time can be fit with the forward shock model, but the radio requires a separate component. And if you propagate that component backward in time, it behaves like a reverse shock. In fact, it shows up in the optical at earlier times. And so that tells us that this polarized synchrotron emission that we are seeing with ALMA is coming from electrons in the jet itself, from this reverse shock. And so we're probing the magnetic field structure of the jet. So let's see how these ALMA polarization observations compare with previous upper limits. So this is the parameter space down here that our observations probe. And so that demonstrates that the challenge is getting on target early enough and with good sensitivity. So we use this measurement to infer the size of magnetic patches in the GRB jet. And this was the subject of the press release that I mentioned in my title slide, which made it into the science editor's pick on Physics World. Now, I don't have time to go into details, but you can ask me later if you're interested about the physical model. And you can also watch this video that's linked from my YouTube channel that we use to explain these results. Now, I'll very briefly show you 2 bits of progress, work in progress, where we're using ALMA to push the frontiers of time-domain astrophysics. The first is this event, GRB 210905A at redshifts of 6.3, which I think is the farthest transient discovered by ALMA.
1 minute.
You can see from this plot that prior to ALMA, we would have no hope of catching the millimeter emission from this event. In luminosity space, we're starting to probe more into the bulk of the population of high-risk gamma ray bursts rather than just the tip of the iceberg, which is all we could do with previous facilities. This is going to be submitted in the next few weeks. And finally, I said I have a surprise for you, and that is that with ALMA, we have just made the first detection of millimeter emission from a short duration gamma ray burst. And this is cool because short GRBs are typically much less luminous by about 2 or 3 orders of magnitude than long GRBs. And only a dozen or so have radio detections, none in the millimeter. Now, we don't have a redshift for this event, unfortunately, but at the median distance of the short burst population, it's more luminous than some of the long burst counterparts. So stay tuned for more updates on this as well. Time-domain astronomy is undergoing quite a revolution, and we'll continue to follow up the most interesting candidates with ALMA from, say, the Vera Rubin Observatory, as well as other facilities, to unveil the underlying physical processes that are powering these relativistic explosions. Now, this sort of science requires managing programs on lots of observatories in addition to ALMA. It's quite intensive. So personally, I'm happy to share that I'll be starting in a few months as a faculty member in the Department of Physics and Astronomy at the University of Utah in Salt Lake City. I have spaces for graduate students and postdocs to join my group. So if you like radio astronomy, which I think is all of you here, all of us here, and if you think transients are cool, then send me a CV, catch me on Slack, or talk to me during a coffee break. I'll stop here. Thank you.
Thank you very much. That was a very exciting talk. It's really cool to see also all these animations. And very well explained. I mean, I'm not an expert on transients, but I feel like I understand more of it now. So thank you very much. Actually, I know that there's a question in the chat, but I'll ask a very quick one. Since I know people that are studying fast radio bursts, is that also, maybe it's not your field, but is that also something that could be done with ALMA?
That is a great question. And the answer depends on ALMA technical capabilities. Like, is it possible to have dump times that are of the order of tens of milliseconds? And if so, then it should be possible to study them with ALMA as well. The trick with fast radio bursts, of course, is we don't know when and where they're going to happen. There are two possibilities. We can either do blind surveys, which is, so the way it's being done at centimeter facilities is using commensal observations. One way of doing it at centimeter facilities is doing commensal observations, where you do fast dumps of the data and search for them in real time. Alternatively, what one can do is look at known repeaters, known fast radio burst repeaters, and then just track them for a certain amount of time. That can often involve looking at just a blank patch of sky for a long period of time. That's not something that I don't know is very easy to do with ALMA. But both of those are potential ways in which one can do. But the primary requirement is rapid sampling from the correlator, and then being able to look through those data in very quickly. So they've over time we've been finding these fast radio bursts at not just at one frequency, not just L band, but at many other frequencies as well. And it's very exciting. It'd be really cool to see them in the millimeter to see what is actually the emission mechanism that is powering these bursts. Great,
thanks. Abhijit, are there more questions?
Yes, there are a couple of questions. So one question is, they wonder whether the red star, the new detection, is that a kilonova?
Yeah, so that's a great question. So let me just go back quickly to that slide, which has that red star on it, so we know what we are talking, what we're referring to. So we're talking about this red star here, which is this new event, which I call the relativistic tidal disruption event. It is actually not just a red star, but it's also red intrinsically. So it's a very red optical spectrum, which suggests that it could be either intrinsically red or it could be coming from a dusty location. Now the exciting thing about that connection to kilonovae is that kilonovae are also red. They are, because they got line blanketing from all these heavy elements that absorb in the blue and in the ultraviolet. Now, the difference, though, is that this event is much more luminous than even typical gamma ray bursts, which are themselves much more luminous than kilonovae. So we are talking several orders of magnitude, maybe about 5 or 6 orders of magnitude in luminosity relative to what we expect kilonovae to be. So the other aspect is that kilonovae, we don't really expect them to produce a lot of radio emission. We expect kilonovae to be mostly producing optical emission from the radioactive decay of these elements that are being produced. On the other hand, when this kilonovae ejecta interacts with the environment, we do expect a shock, and we do expect emission from that. And that is we may have the first evidence for some of that shining through in the X-rays at very late times in the one event for which we do have we have a clear kilonova, which is GW170817 or 8017 GFO. And that's at 1,000 days after the explosion. It's very deep Chandra observations, and that event was much closer than this event. So So the answer, the short answer is no, but I think I've given you the explanation for why.
Excellent, thank you. There is another question if we have time for it. Is the reverse shock brighter in submillimeter than the forward shock? And if so, why?
The reverse shock the answer is yes, the reverse shock is bright in the submillimeter. Let me go quickly back to the slide that has a plot on it, which you can see. So the reverse shock is over here, the forward shock is over here. You can see that the reverse shock is indeed brighter. And so the reason is that the emitting region is denser, and because it's the jet, and the jet is typically denser than the surrounding environment. So there are more electrons that, or the fewer electrons get more of the energy from the shock and are able to radiate with the higher flux. And in fact, the ratio of the peak flux of the reverse shock to the peak flux of the forward shock is related to the Lorentz factor of the outflow. And this is one of the ways in which we can measure the Lorentz factor of the outflow, is if we measure the locations of these breaks and the peak fluxes of the two components.
Sounds great. I think we have a bit of time from the previous talk. So if there's another question, I think we can take that.
A new question just came up. How is ALMA triggered shortly after the GRB event? Do these observations always have priority?
That's a really fantastic question. Let me go back to the first ALMA light curve of a GRB, where we had, we've been working with, let's see, so go to the slide, yes. So we worked with ALMA, the observatory and GEO, to try to do this as quickly as possible. So the answer is, as far as I know, the observations don't have priority or any more priority than any other kind of observation. So they're graded the same way, you know, grade A or grade B or however, once they're accepted. So we go through the same proposal process. When we submit a trigger, then the observations, because we don't know the target location in advance, so once we have a target, we submit a trigger, and then it's up to the scheduling process to figure out when it's going to be observed. So in the past, we had this issue where we didn't know when we were going to be able to get the data, what was taken what was in the data, because we often get, as you can see, multiple epochs, because we want to track the evolution of the source or the luminosity as a function of time. And to do that, we first want to know if there is any detection in the first epoch, because otherwise we might just be wasting observatory resources. So what we wanted to do was have access to the raw data right away. And so now, through our work, we're able to we brought about a global change in policy at ALMA, where PIs of time-domain projects are now given access to the raw data right away. And that helps us assess whether we want to continue follow-up observations with ALMA, whether we want to trigger follow-up at other facilities in the centimeter band or in the X-rays, and that's not something that was easy to do in the early ALMA cycles. But apart from that, the scheduling goes as a regular scheduling. If somebody from ALMA has more information than this, I'd love to know. But apart from that, it's just we submit a trigger and then hope for the best.
Great, thank you very much.